Dear students, welcome to this session on coordination chemistry. In this session, let me discuss valence bond theory. This valence bond theory was proposed by Linus Pauling. According to this theory, the bonding between ligand and the metal atom, that is the bonding between, say, the ligand and the metal atom is purely covalent in nature. So this covalent bond is formed as a result of overlapping of the completely filled ligand orbitals and the vacant metal orbital. Now the main assumptions of this theory. So the first assumption will be, so the bonding between the ligand and the metal atom is purely covalent in nature, and this covalent bond is formed as a result of sharing of electrons between, say, completely filled ligand orbital and a vacant metal orbital. That is the first assumption. Then second assumption is that each ligand must contain one filled orbital to donate the electrons to the central metal atom. So each ligand must contain a minimum of one completely filled electrons to donate to the, say, central metal atom. Then third assumption will be the central metal ion or central metal atom must contain or must have vacant orbitals, and that vacant orbital should be equivalent to that particular central metal's coordination number. So as I mentioned again, the second assumption, each ligand must have a minimum of one completely filled electron to donate to the central metal atom, and the third assumption is that the central metal atom must have vacant orbitals so that it can accommodate the electrons donated by the say ligand orbital, and that number of vacant orbitals in the central metal atom should be equal to its coordination number. Then fourth assumption will be, they say vacant atomic orbitals in the metal undergo a process called hybridization, they say. So the vacant metal orbitals in the central metal atom undergo a process called hybridization. What is meant by hybridization? So the atomic orbitals which differ in the energy undergo a process called hybridization to give rise to equal number of hybrid orbitals which have, say, equal energy or which have same energy, we can say. So let me repeat once again. The vacant metal orbitals undergo a process called hybridization when several orbitals which have got different shape, different size, different energy, it undergoes a process called hybridization to give rise to a new set of orbitals called hybridized orbital which have same energy, or we can say which have equivalent energy. That will be the fourth assumption. Now the fifth assumption is the hybridized orbital, or we can say the hybridized metal orbital, have better directional character. As a result of that, the hybridized metal orbital now overlaps with a completely filled ligand orbital, as a result of which they say a ligand metal coordinate covalent bond. I mentioned a word now, coordinate covalent bond. Again, this is a type of a covalent bond to give rise to a coordinate covalent. They say a sigma bond is formed. A sigma bond is a rather strong bond. So here the hybridized vacant metal orbital will form a coordinate covalent bond with the ligand atom or with the ligand orbital, resulting in the formation of a coordinate covalent sigma bond, they say. Coordinate covalent bond is a type of a covalent bond where both the shared electrons come from the single atom, that we already learned in the lower classes. Next assumption will be, see, the hybridized orbital, just now I mentioned that the hybridized orbital have better directional character, therefore they orient in different directions in space. So their orientation gives rise to definite geometry for the complex compound, they say. Now we have in the book, we have got a tabular column which states like this. See, coordination number, hybridization and geometry. When the coordination number is 2 and if the hybridization is sp, the geometry will be linear. Likewise, they have given for 3, hybridization will be sp2, then the geometry will be trigonal planar. Likewise, for 4, if it is say sp3, then the geometry will be tetrahedral. If it is for 4 and if the hybridization is dsp2, it is given as, say, square planar. And if it is for 5, that will be dsp3 hybridization, then the geometry will be trigonal bipyramidal. Likewise, for 6, we have two types of hybridization, sp3d2 and d2sp3. For both, the geometry will be octahedral. So this is the tabular column given, which corresponds to coordination number, hybridization and geometry. So this easily you can explain. And then what they say, in an octahedral complex, if say inner orbital, or they are given one word, if n minus 1d, that is in an octahedral complex, if n minus 1d orbital or inner orbitals are involved in hybridization, then such complexes are called as inner orbital complexes. Inner orbital complexes. Let me explain once again. In an octahedral complex, if n minus 1d orbital or inner orbitals are involved in hybridization, such complexes are called as inner orbital complexes, which can also be called low spin complexes or say spin paired complexes. You can easily remember the word say LSP, that is what I used to remember. So LSP stands for say low spin pair, LSP. In some way you can remember. So the inner orbital complexes can also be called as low spin complexes or spin paired complexes. Now, in another way, in an octahedral complex, if say ND orbital or outer orbitals, inner d orbital we can say, outer d orbital. So in an octahedral complex, if ND orbitals or outer d orbitals are involved in hybridization, then that complexes will be called as outer orbital complexes, or they can say high spin complexes, or I can say spin free complexes. So this you can remember the word HSF. HSF. High spin complexes or spin free complexes. This one is low spin complexes or spin paired complexes. So in this way we can explain that. Then other assumption is like this. Now the next assumption states like this. That is, in a complex, they say if unpaired electrons are present, such complexes are paramagnetic. Suppose if in a complex there are no unpaired electrons, such complexes are called as diamagnetic. Okay, let me repeat again. In a complex, if there are unpaired electrons present, then such complexes are paramagnetic in nature. And in a complex, if there are no unpaired electrons, such complexes are called as say diamagnetic in nature. Next one will be, say they are talking about some ligands. Some ligands say En, which stands for ethylene diamine, then NH3 is for ammonia, then CO, this is for carbonyl, then Cn minus, this is cyanide. So these are ligands. No, ligands are donors of electrons, that we know. When these ligands are present, what these ligands will do, this will try to pair the electrons present inside the complexes. If there are any unpaired electrons present, these complexes, if it is present in the complex, these ligands, what it will do? It will push those singly filled electrons to pair up inside. So these ligands are termed as strong field ligands. Okay. So these ligands are strong field ligands because it pushes or it pairs the singly filled electrons to pair up inside in the complex. Then the last one, what they say, last assumption is like this. Greater the overlapping between say a completely filled ligand orbital and the vacant metal orbital or the hybridized metal orbital, greater will be the bond strength. That is, if the extent of overlapping is greater, then the bond strength will be greater. These are all the postulates according to Linus Pauling, and this is what we call it as the assumptions. Let me repeat once again. These are assumptions of VB theory. Now let us learn the advantage. There is only one advantage in this valence bond theory. The first advantage is that it is possible to predict the geometry of the complex based on their say magnetic behavior, or we can say from their magnetic behavior, it is easy for us to say predict the geometry of the complex. So then three limitations are given. Limitation number one, it does not explain the color of the complex. So that is the first limitation. So this valence bond theory does not explain the color of the complex or color of the coordination compound. Second limitation is it does not explain quantitatively why certain complexes are inner orbital complexes are outer orbital complexes for the same metal. Let me give this example. See, for FeCN6 3 minus and FeF6 4 minus. Now you can see in both the cases the metal atom is Fe, but this complex is inner orbital complex, whereas this complex is outer orbital complex. The reason is not clear, or the valence bond theory is not able to give proper explanation for this type of complexes given by the same type of metal. Then the third limitation is like this. This particular valence bond theory considers the spin only magnetic moment. It does not consider other components of the magnetic moment they are given. So it considers only the spin only magnetic moment and does not consider the other components of the magnetic moment. So these are all the three limitations according to Linus Pauling in the valence bond theory. Now let us learn the illustrations what we have discussed. To see, I mentioned you some of the assumptions. Now those assumptions will get clear if you observe the illustrations given here. Now here I have considered two complexes. One is NiCN4 4 minus and NiCO4. So this is, in this case you can see nickel is the metal atom here. We know that the atomic number for nickel will be 28. So the outer configuration will be 3d8 4s2 that I am drawing now. So 1, 2, 3, 4, 5, 6, 7, 8 and 4s2 electrons are there. This is the actual configuration of nickel. In this complex, the oxidation state of nickel is Ni2 plus. These two electrons are lost from this s orbital and therefore the complex is like this. So this one is the electronic configuration for Ni2 plus. So 3d8 4s0. In the complex you can see here the ligand is Cn minus. Now we know Cn minus is a strong ligand. So when the Cn minus enters into the complex, what happens is that it pushes the unpaired electrons present in the orbitals to pair up inside. As a result of that, you can see 1. So here this electron will be pushed to pair with this single field electron. As a result, you can see there will be one vacant 3d orbital. So in this vacant 3d orbital, what happens is that, see, this one is Cn, 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 Cn. You can see in, say, one d orbital is there, one s orbital and two p orbital. So one d orbital, one s orbital and two p orbitals are involved in hybridization. As a result, the hybridization that is involved here will be dsp2 hybridization. So if the hybridization is, say, dsp2, then the geometry will be square planar. This is what we have discussed in one point. So since one d orbital, one s orbital and two p orbitals are involved in hybridization, the hybridization is dsp2 and therefore the geometry will be square planar. Okay. Now let us calculate the value of n. So here you can see n is equal to 0. So what does n represents there? N represents number of unpaired electrons. So here there are no unpaired electrons and therefore n is equal to 0. Therefore mu s is equal to square root of n into n plus 2. So much Bohr magneton. This is the spin only magnetic moment formula. Now when I substitute here, since the value of n is equal to 0, mu s is equal to 0. Therefore, since there are no unpaired electrons here, we have learned in one assumption that when there are no unpaired electrons in a complex, then the complex will be diamagnetic. So as a result, since there are no unpaired electrons here, this complex is diamagnetic in nature. Okay. So their magnetic moment is also equal to 0. Now let us come to this another one example, NiCO4. So here the configuration of nickel is 3d8 and 4s2 as we have discussed earlier. 1, 2, 3, 4, 5, 6, 7, 8 and it will be 2, 4s2. What we have to observe is here nickel, oxidation state of nickel is 0. Okay. So since the oxidation state of nickel is 0 here, no electrons are lost like what we have discussed here. So these two electrons will be there as it is. Now when CO is a carbonyl ligand, this is again a stronger ligand. Now when this carbonyl ligand enters, what happens? It pushes the 4s electron present here to pair with these two electrons. Okay, so in the electron it comes over here. So as a result of that, this complex will look like this. So this electron will come over here, and for a change I am writing, you see, CO, 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 CO. So these two electrons will come here. So this one will come over here, this one will come over here. As a result of that, you could see there will be 4 CO ligands, and here you can see one s orbital is involved in hybridization and 3 p orbitals are involved in hybridization, and therefore the hybridization will be sp3. We have learnt in the assumption that if the hybridization is sp3, automatically the geometry would be tetrahedral. Okay. Again, here n is equal to 0. Why? There are no unpaired electrons, and since n is equal to 0, mu s is equal to 0 like what we have discussed here. Again, here there are no unpaired electrons, and therefore this molecule is also diamagnetic. Hope you have understood what I have said here. Now let us discuss. In an octahedral complex, we mentioned in the assumption that if say n-1d or inner orbitals are involved in hybridization, such complexes are called as say inner orbital complexes. And in an octahedral complex, if outer orbitals or nd orbitals are involved in hybridization, I mentioned that such complexes are called as outer orbital complexes. Let us learn about that by considering FeCN6 3- and COF6 3-. These two are the apt examples. See, for iron, the atomic number is 26, and therefore the outer configuration will be 3d6 4s2. So you can see 6 electrons in the orbital. So 1, 2, 3, 4, 5, 6, and there will be 2 electrons in the s orbital, 4s orbital. So this is the say electronic configuration for Fe. In this complex, the oxidation state of Fe is 3+, and therefore 3 electrons are lost. So as a result of that, 2 electrons from this s orbital and 1 electron from d orbital will be lost. As a result, you will have only 5 electrons in the d orbital like this. 1, 2, 3, 4, 5. There will be no electrons in s orbital, and there will be only 1 in the this or d orbital here. As a result, the say electronic configuration will be 3d5 4s0 for Fe 3+. Now, when the ligand say Cn- approaches this particular say hybridized vacant metal orbital, we know that Cn- is a strong field ligand. So what this will do? This will push the 3d orbital singly filled electrons to pair up inside. So you have totally 5 electrons here. You see 1, 2, 3, 4, 5. So all these 5 singly filled electrons will be paired up like this. Leaving behind, see, you have say this is actually 3d, this is 4s, and this is 4p. This is one Cn, Cn, again Cn. So 6 Cn- ligand will give its electron like this. So Cn being a minus being a strong field ligand, it pushes the singly filled electrons present in the 3d orbitals to pair up inside. As a result of which you get this kind of arrangement. Now you can see that 2 d orbitals, 1 s orbital, and 3 p orbital will undergo hybridization. As a result, you can see d2 2 d orbital, d2 1 single s orbital, and 3 p orbital. As a result of this, say d2 sp3 hybridization will be observed here. As a result, we know the geometry will be octahedral. So here you observe the inner d orbitals are involved here. See, if you observe, the n value is equal to 4 here. Here I mentioned this n here like this, and this principal quantum number n. If you compare pandrappo, this will be 1 number less. As a result, that's what I mentioned. If n-1 d orbitals are involved, that n-1 represents here this is considered to be n. So this 3 will be n minus 1, and therefore these orbitals are called as inner orbital complexes. Now the value of n is equal to 1 here. This n is different here, just have a clear understanding. Now this n represents the number of unpaired electrons. So one unpaired electron is there. Therefore mu s is equal to square root of n into n plus 2, that is equal to root of 1 into 1 plus 2, that is equal to root of 3. So the value will be 1.732, so much Bohr magneton. And also you can see here, we already learned that in a complex, if there are single-filled electrons or if there are unpaired electrons, the magnetic character will be paramagnetic, we have learned. So this is paramagnetic. Now let us come to this particular example. Cobalt F6 3 minus. See here, the say atomic number for cobalt is 27, and therefore the normal electronic configuration will be 3d7 4s2. So I am drawing like this: 1, 2, 3, 4, 5, 6, 7, and 4s, 2 electrons will be there. Now the oxidation state of cobalt in this complex is 3 plus, and therefore 3 electrons are lost. Those 3 electrons are lost like this. See, 1, 2, 3, 4, 5. Only 1 will be here. There will be 4 unpaired electrons present here. Now this F minus ligand is rather a weak ligand. So this weak ligand, no, this will not do like what this Cn minus has done. So this is a weak ligand, and therefore what happens now? You see, this F will give its shared pairs of electrons like this. So where there are vacant orbitals, there electrons will be donated. Now you just observe here, 1 s orbital, 3 p orbital, and 2 d orbitals. You can see sp3 d2 hybridization is involved. We have learned there the assumption that if the hybridization is sp3 d2, then the geometry will be again octahedral. Now you have got to observe here which d orbitals are involved in hybridization. Outer d orbitals are involved in hybridization, or I can say n d orbitals are involved in hybridization. This n corresponds to this n. Here you see n minus 1 because 3d orbital. So when outer d orbitals or n d orbitals are involved in hybridization, such complexes are called as outer orbital complexes. Okay. Now what will be the number of unpaired electrons here? 4 unpaired electrons are present. Therefore apply the formula. Mu is equal to square root of n into n plus 2, that is equal to square root of 4 into 4 plus 2, that is equal to root of, say, 4 into 6 will be 24. So the answer will be somewhat around 4.89 Bohr magneton. Again, this is the magnetic moment value, and since there are unpaired electrons present, this molecule will be like say paramagnetic. So in this way we can explain the say inner orbital complex and the outer orbital complex. So in this session we have discussed valence bond theory with the illustrations. Hope you understood what I said. Thanks for watching.